Hello, and welcome to today's webinar, Development Trends and Challenges for UAV Inspection Applications. This is brought to you by our sponsor, Septentrio. I'm Allison Barwatz from North Coast Media, Senior Digital Editor for GPS World Magazine, and I will be your event manager. Before we begin, I'm going to go over some ways that you can participate during today's presentation. Although you are currently in a listen-only mode, we encourage you to ask questions throughout the presentation. Just type in the text box at the bottom left, then click Submit to place your question in the queue. You can also submit questions via Twitter by using the hashtag GPSWorldWebinar. Questions that were submitted during registration have already gone to our panelists and may be covered in this webinar. Some questions may also be answered in an upcoming issue of GPS World Magazine or in one of our e-newsletters. We strive to answer as many of your questions as possible. If you experience any technical difficulties during today's event, use the same Q&A box at the bottom left to tell us about your issue and click Submit. And Assistant Producer Grace Ryback-Rye will personally assist you. Finally, a recording of this webinar will be available tomorrow afternoon at gpsworld.com/webinars. You can get to that page now and bookmark it by clicking on the GPS World logo in the top left-hand corner of your console. A link to the on-demand recording will also be emailed to you tomorrow. Now, I'd like to turn today's event over to our moderator, GPS World Editor Alan Cameron.
Thank you, Allison, and hello, good morning, good afternoon, good evening to all of you around the world. I'm glad to see that once again we have an international audience. We have a very exciting webinar for you today, Development, Trends, and Challenges for UAV Inspection, brought to you by Septentrio, a designer and manufacturer of high-accuracy GNSS equipment, headquartered in Belgium with operations and clients around the world. We're going to hear from Septentrio directly and from some of their clients who are doing some exciting things with UAVs and GNSS and other sensors, cameras primarily, around the world. I will be your moderator, and I will return at the end of the presentations. We have 5 presentations to field some of your questions. I have a short list of questions submitted by attendees prior to the webinar, and as Allison said, we encourage you to submit questions during the webinar, and we'll get to as many of those as we can. Today we'll hear first from Gustavo Lopez from Septentrio. He'll take us through an overview of the transition underway between simply flying cameras aboard UAVs to smart sensors and really highly enabled applications in the field. Following that, we'll hear from Todd Humphreys regarding large-scale centimeter-accurate collaborative mapping. John Laxson from Kespry about high-accuracy GPS in aerial and UAS applications. We'll see some exciting footage from a company called Flying Cam that's been responsible for some of the aerial effects and recordings in a very popular television series and a recently released movie. And finally, from Flavien Viguier from Altametris, a company associated with the French railway system, talking about use of UAVs and filming in infrastructure and other applications. Right now, without further ado, let's hear from Gustavo Lopez at Septentrio.
Thank you very much, Helen. Hello, everybody. I'm Gustavo Lopez. I'm the product manager for UAS applications at Septentrio. And I want to start with this picture. And I think everybody of you have seen this picture before. And this is a picture in New York, somewhere around the 1930s. So you have to imagine that this is just after the Depression. But I want you to think what these people were actually doing. And you have to, of course, they are having some lunch here, which is a definitely nice picture behind it. However, these people were doing a very high construction of skyscrapers. And this is basically something that takes me to drones. Drones are basically something that we want them to fly very high in order to perform different type of jobs. But these people were not only, of course, doing the inspection of the construction, they were also doing the actual job. And I think this is one of the things that drones will start to do more and more. And basically, this is something that I call crossing the chasm. And I think we have already seen many drones in mapping areas, and this is actually already very popular. Having a PPK drone with centimeter accuracy, that's already something that we get to see in the mapping side. But in the inspection side, we also see that people are requiring more and more accuracy. And this is actually moving towards that basically right side, which is bringing smart sensors, which can also do field actions in the job itself. So it's not only, again, about inspection, but that I believe that more and more we will get to see drones doing actual jobs. Of course, when we are talking just in the inspection side, we are talking that many companies have to go to different challenges. Of course, we are talking about business challenges, but also technological challenges. Some of the business challenges are, of course, in the cost side. People want to have cheaper and cheaper technology to have that. Sensors are becoming also cheaper as well. And of course, there is an important aspect, which is the ethics and privacy side, and of course, all the legislation aspect of that. And this is because when we are talking about inspection drones, we are talking about that all these drones are working in cities where people are basically just next to them. And this is an important aspect of the inspection side. And of course, that brings also the business adoption is also a challenge. So again, I see the different type of technology that is taking us from just having an inspection job, which now is already an easy workflow for many people, and from the image processing side. But I see that people are more and more bringing more evolution in the sensor side, making it easier for people to take decisions. And people are asking us more and more for reliable technology. It's not only basically any drone that can do an inspection. They want to make sure that the platform is reliable enough for this type of jobs and applications. So again, it's not only about doing inspection. Here you have basically a great example where you can see not only the people basically making the inspection, but actually doing the actual job of the infrastructure. And this is what we will get to see more and more in terms of technology. When we are talking about drone generations, of course, we all know that we have the multi-rotors, and those were the first type of drones that were in the market. But we also have the fixed. And the fixed-wing drones, they can go far distances. They can help us to beyond line of sight flights, so ideal for many type of inspections. And we get to see now more and more VTOLs, basically the technology of both multi-rotor and fixed-wing in a single combined hybrid technology stack. But what I get to see as well is actually the drone that you have at the bottom here, which is a drone that is getting ready to actually do the work in the infrastructure itself. And what is the difference? Basically, you can see that the rotors, they have the capability to have pitch, yaw, and roll, basically the three orientation, making it much easier to get closer and closer to the infrastructure. So this is, of course, technology that we will get to see more and more, but definitely is very interesting to have that as well. When we are talking about technological challenges on the inspection side, and when we are talking to the different customers that we have with drones, people come with the following challenges. They are telling us they want to have a reliable, relative, and also accurate position inside. So again, it's not only that people want to have the centimeter level accurate position, absolute position. People also want to have a relative accurate position. It's also very interesting. And then, of course, when we are talking about inspection, then the orientation of the drone is also quite important. So this is something that we have seen more and more, and that we get to see. It's not only about position, it's also about orientation aspects. People want to have fail-safe systems. That means, of course, not only, and I have seen many drones not only using one single GPS, they might be using more than one single GPS on their platform as well. They want to be efficient, and this is basically when we are talking about the attitude information of the drone itself. They want to make sure that also that the technology is efficient also with robustness in vibration side as well. They want to work in different environment conditions. We are talking about doing inspections in all type of weather conditions, so that's also quite important, and we get to see it more and more. We want to, of course, reach further and further distances, and I think we have an excellent example in this webinar that will be presented as well. where people want to reach longer distances as well in long length of sight. People, of course, at the moment they are working these faraway distances, they also want to be able to transmit data. And then that takes us to the aspect of communication. They want to be able to transmit small chunks of data in a compressed way as well. We get to see more and more sensors as well that are trying to avoid, of course, crashing into obstacles, because we are talking about drones that are closer to infrastructure as well. And then, of course, we are not talking about a single drone, but we are talking about multiple drones that could be doing the job. And they might be connected also to a control center. And this is where we get to see the challenge, basically, of the question for having a network-centric infrastructure. When we are talking about the GNSS technology and how can a high-end GNSS receiver can help there, of course, we have to think that RTK will help. That's basically the accuracy side of it. But as I mentioned to you, it's not only the RTK side. People want to have sometimes a relative accuracy as well. In that aspect, they could also be using other techniques such as moving base or other GNSS aspects as well that can help them there. People want to work in many occasions without corrections. Again, if they are basically traveling far distances, they want to have still a reliable or an accuracy that is good enough in order to have sites without sending corrections in other precision. We see again, we want orientation. So a GNSS receiver with a dual antenna can definitely already help, but a GNSS INS combined system will also help to provide the 3D orientation angles as well, which can be important, of course, for the camera orientation side, but also for the point of interest of the job itself. We get to see that there is more and more requests for low power. Again, if you are talking about a drone that has to do a job itself of inspection, we are talking about long duration jobs, then people want to have a low power. And many people think, okay, 1 watt of power is basically already excellent, but when we talk about 2 watts, people think, it's not a big difference. But actually, it can make a big difference because there is dissipation on the electronics of the drone, which will definitely reduce the battery life as well. Even if most of the drones that I have seen, they are actually doing real-time inspections in order to have the precision real-time as well, the reliability real-time, there is still the aspect of post-processing. Many people are still doing geotagging of the inspection job itself to have the accuracy element as well. When we are talking about networking, then you have to talk about a GNSS receiver that is also ready for networking. And in that case, is also ready to communicate to other type of sensors. And of course, we are talking about the communication to events, the PPS synchronization for timing, but also in order to be able to communicate via networking. In that case, we are talking about Ethernet or IP protocols that make it very easy for people either to transmit corrections or even just to transmit information of the position between the different drones. Reliability is the more important part that I get to see as a request. Again, these drones are working in very dense areas, which basically means that people are looking for a reliable hardware platform behind, and they want to make sure that there is no jamming of the GNSS receiver, that there is no spoofing, and they want to have, of course, some level of redundancy. And here also, a GNSS INS technology can also help. And environmental, of course, we have to make sure that a GNSS receiver is also robust against different type of temperatures, but it's also robust in the vibration side. And there are different algorithms in GNSS that can help you to still keep a very good position even when you have vibrations. When we are talking again about the reliability part, especially when we are talking about the jamming side and the spoofing side, people want to be able to monitor that interference. They want to be able to realize that there might be a jamming, and they might be careful in that inspection side. And they want to also, if possible, to mitigate this automatically. And they also want to, of course, avoid, if possible, anti-spoofing. And I can tell you there are technologies that you can buy for $50, which will allow you to have already problems in GNSS receivers. So having a high-end GNSS receiver that can cope with this type of technology is not easy. You have to have technology that is prepared not only in software level, but also in the core hardware side of it in order to avoid interference mitigation. And in this case, Septentrio has the AIM Plus technology that can help in that aspect. So actually, these are some of our GNSS receivers here in Septentrio, and these are the more common receivers that we get to see in the drone industry. We have, of course, a single antenna receiver, which is an RTK, PPK type of system. We have a dual antenna that can help, of course, in the two-angle orientation and can help especially when you have problems with other sensors that can be susceptible to magnetic interferences. And then we have, of course, also a UAS system that makes it very easy for people to integrate into their drones. And at the end, we have a GNSS INS system that combines basically both the RTK positioning side, but also gives you precise orientation out. And we are given, of course, the flexibility because we have a geotags library that allows you to do the post-processing after. So I think, well, I pass it now to the rest of the speakers. They have excellent presentations and very good examples on how actually GNSS is helping them in the type of job.
Thank you, Gustavo. We're going to turn now to recent work at the University of Texas Radio Navigation Laboratory, presented by Todd Humphreys, a frequent author in GPS World Magazine and webinar presenter. Todd, please go ahead.
Thanks, Alan. This is Todd Humphreys, and I'll be reporting on work that my student Tucker Hayden has been leading at the University of Texas at Austin. The goals of our work are laid out here, but I'll only be touching on 3 of these goals. Kind of working clockwise from the upper left, we want to do mapping in 3D, and we wish to do this with multiple drones. We'd like the mapping to be collaborative across the drones. We'd like it to be also highly accurate. So as you move to the right, sub-decimeter location accuracy of map features. We want every one of the 3D points in the map to be within decimeter accuracy, or even better, within centimeter accuracy. And we want to do active sensing. That is, that perhaps the most novel approach in our research is that we want the drone swarm or the group of drones to know about the accuracy of the three-dimensional map that's being created, to have a sense of the accuracy of that map, and to take actions to improve that accuracy over time. The other goals here are longer-term goals. I won't go into those, but you can read about them in the slides as they are given to you later on. I'll only have 2 equations in my slide, so this is the first one. I just wanted to remind people that what's being done with a camera as it's flying around on a drone is three-dimensional reconstruction of a scene, and it's based on mathematics that has its origin in photogrammetry and also computer vision. The so-called structure from motion problem is to simultaneously determine the three-dimensional location of all of the feature points that can be extracted from the images, and to determine the camera location and orientation as the images were taken. And this is done using what's called a bundle adjustment algorithm. And what you see here is the cost function for that bundle adjustment algorithm. Inside the double sum end, you see that the pi function is taking in the camera positions, the camera orientations, and the three-dimensional points, and returning a two-dimensional point that is supposed to be close to the feature point as seen on the image plane of the camera. And this gets subtracted from the actual measurement and squared, and that becomes, when added all up, the cost function. The bundle adjustment that we're applying, that Tucker is applying, is a fairly straightforward extension of this that incorporates the GPS measurements directly into the bundle adjustment. And this is a smart thing to do if you're flying around with a UAV that has highly precise GPS. In our case, we use RTK GPS that provides us centimeter accurate knowledge of the location of the UAV. And so by incorporating the precise position of the camera every time an image is taken, you're able to render the three-dimensional model in global coordinates with high precision. And this allows you to have all of the scaling right, all of the orientation right, and to fuse together multiple maps created in the same way. So let me give you an example. This is our so-called sensorium system. It's part of the work that my students are conducting in self-driving cars for perception research. And you can imagine that perhaps this self-driving car approaches an intersection and finds itself with too much risk in the intersection to proceed at its usual speed. Perhaps there are some blind spots, perhaps this is a known problematic intersection, and the sensors on the vehicle are simply not enough to eliminate all of the risky blind spots there might be lurking there. And so you could imagine having a little payload on the back of the sensorium. In this case, it's our drone payload that could be deployed as a reconnaissance vehicle and fly around the intersection, mapping it and sending data back to the sensorium. The idea would be that you would have, as shown in this image, a UAV that has precise accuracy given to it by RTK GPS. In our case, we use two antennas, both for orientation and for anti-spoofing. And this small UAV could be deployed from an automated vehicle, fly around an area. In this case, we're using the object you see in the foreground as a stand-in for whatever wishes to be mapped. And then we are producing maps with a single camera. It's a 4K camera, so it has high resolution. But I want you to take a moment to appreciate how beautiful the three-dimensional map is that gets produced. This is not a photograph. This is a still taken from software that does the three-dimensional rendering. And it is a three-dimensional map. This is a map, not a photograph. It has resolution at the millimeter level and centimetric accuracy with a global relevance. So this isn't centimeter accurate only with respect to the vehicle, but also it's centimeter accurate with respect to the global reference frame. One of the goals of our project is to ensure that the map is as accurate as we're claiming. So, for example, what if the requirement were that every feature in the map that we produce is accurate to within 10 centimeters? How do you know if a feature is accurate to within that amount? One way is to look inside the covariance matrix produced in the bundle adjustment and examine the formal errors associated with each one of the three-dimensional points. On the left, you see that the points painted in green are those falling below formal errors of 1 centimeter, and the points painted in red are those that exceed 1 centimeter formal errors. And on the right, you see a histogram of the errors. The red line indicates 1 centimeter, and so most of our errors are less than a centimeter, but you might have places where the map is weak due to too few images being taken in that area. Our long-term goal is for the UAVs, the squadron of UAVs, to recognize this fact on the fly and take further imagery to address the weakness in the three-dimensional map. How to scale this up? How to make this practical for something the size of a building or a campus or perhaps an entire city? Well, the key is to not do standard bundle adjustment all the way through. That is, the key is that you don't wish to do what is called incremental bundle adjustment, adding one new image or one new keyframe to the millions you already have. Instead, you would want to divide up your map and conquer it in a divide and conquer fashion. And that requires you to do separate processing on subsections of the map, but then to blend all of those subsections together into a unified map. And we view the key to this is RTK positioning, because that allows you to blend together two independently created maps at the centimeter level. On the left here, you see these were 400 images taken and fused together in a unified iterative bundle adjustment. On the right, you see that we split these images into two sets of 200 images, and we performed the same batch bundle adjustment on both sets independently and then fused them together, and the scene is accurate at the centimeter level. So we believe that high precision GPS is really the key to making this scalable. You could send out a swarm of 10s or even 20 UAVs to map an area, each of them takes care of a smaller area, and then the fused map is produced in the end. Looking forward, we care to solve this so-called next best view problem. We want to know if we have a given map with a certain level of accuracy for each one of the feature points, what is the next best view of an image that could be taken to improve the map accuracy in those areas where it lies beyond our accuracy threshold. So if we want 1 or 2 centimeter accuracy for each one of the feature points, but we have a few feature points that are outliers, what kind of imagery could we take? What pose of the UAV is the right one for snapping a new image that could be brought into the bundle adjustment and improve the accuracy in the problem areas? Solving this is not easy. It turns out to be an NP-hard problem, figuring out what the next best view is. But my student Tucker is working on that, and we have every hope that we'll have a smarter, swarm-based mapping system that can be deployed in the coming years. Thanks, and I'll transition on to the next speaker.
Thank you, Todd. We're going to hear now from John Laxson at Kespry. Kespry is a company that specializes in drawing insights from 3D and geospatial data, and in particular applications with inventory, earthworks, and property inspection. John, please go ahead.
Good morning, afternoon, or evening, everybody. As Alan said, I just want to talk a little bit about Kespry and then our positioning solution and how that plays into many of our kind of end applications and data solutions. The most important thing to know about Kespry is that our whole business focus is getting actionable data and insights to our end users. We treat the drone as an important component of that, but we're very much focused on the vertical integration of planning to capture to analysis to business specific delivery. We started out 4 years ago building a drone of our own because there was no platform that let us deliver the experience that we want. And as we've learned over the years, the positioning solution, specifically GPS for us, not only plays an important component, but represents a number of challenges that solving well enables upstream. So this is the Kespry 2 and 2S drone. The important components are we have a completely integrated Sony integrated lens camera. We have a single-dimensional LiDAR that we use for obstacle avoidance. We have, on this system, a Septentrio Asterix GPS module that we use in several configurations I'll talk about. And the drone has on board a Intel quad-core CPU with integrated GPU. And some of the peripherals that we integrate rely heavily on that. For example, USB 3 for image and LiDAR stream capture, for example. And that provides an interesting challenge on the USB front, because USB 3 has a lot of noise, or emits a lot of noise in its transfer spectrum right in the 1.5 gigahertz. And so we've learned over the years that the drone ends up being its own best jammer. And we have applied the Septentrio system both to support development, and it's robust to some degree to any leakage from the onboard CPU system itself. But the Spectrum tools also are important during the development phase because they save a lot of work, bringing the drone into a test environment. So a little bit about the Kespry applications, and I will talk a little bit about our specific positioning challenges in each of these. So we're active in the aggregates market, and the principal use case here is monitoring the quarry status and stockpile inventory for aggregates like asphalt and concrete production. We also do earthworks and survey, where our goal is to provide sub-decimeter, usually on the order of 2 to 3 centimeter accurate surfaces of earthwork sites that can be used either in bidding and planning excavation or in monitoring site status. And the last is in structure and property inspection, where you want to operate the drone in tight environments and get both relatively accurate or high relative accuracy data and operate both close to buildings and near obstructions, and having a stable positioning reference becomes critical. So our first unit shall talk about the aggregates and inventory. We are looking to do stockpile inventories to within about 1% across volumes of 1 to 5 cubic meters to thousands and tens of thousands of cubic meters with stockpiles, single piles valued in the hundreds of millions of dollars sometimes. And the solution that we bring to market right now, as I mentioned, is the Asterix M2, using SBAS or standalone modes with basically all-in-view satellites and multiband. And this, on its own, gets us usually 30 centimeter absolute accuracy and high scale variation, and that, or high scale accuracy, and that low scale variation is what enables us to do the high accuracy volumetrics from day to day, month to month. The second application in earthwork survey. This is typically done these days with a manual surveyor, perhaps a 2-meter survey pole, walking around and taking individual points. We aim to replace that with a drone survey that can do hundreds of acres in less than an hour. However, the needed accuracy provides a challenge. And so here we add post-process kinematic data to the solution. And we usually have the customer tie in a existing known survey point for the base, and then perform the correction after the drone flight. One of the issues in some of these sites with a high amount of industrial equipment operating are that the 900 megahertz and 2.4 gigahertz ISM bands that are often used for drone communication can be congested and busy. And an RTK solution frequently depends on those to get correction data in near real time to the drone. So using the post-process data stream means that we are not dependent on any real-time communication for the final accuracy of the system. One of the other things that we had focused on bringing in collaboration with Septentrio is that all of the GPS internals are completely embedded in the Kespry system. So using the base, once the data is captured, you simply plug the base station in with USB to the Kespry ground station, and integrated with Septentrio's software, we will pull automatically the required data for reference calculation, upload it along with the imagery to Kespry, and perform all of the post-processing and RTK calculations in the cloud, where we can monitor and support it. So the user ends up not requiring any specialized GPS knowledge. The last challenge in property inspection, and this is a place that we're actively working on new development with Septentrio. More so than the relative accuracy, which is, we hope to get similar performance as I mentioned in our aggregate. We have the drones operating in tight environments, and so I tried to pick two pictures here that show how close to hard structures that our customers are operating. These tend to be high multipath environments, and during flight, drifts of even a meter or two can cause property damage either to the drone or to objects near the takeoff location. So having high, during flight, relative accuracy to come back to home has been critical for us. And we are currently in the final testing phases and hope to be rolling out soon a return-to-home solution that Gustavo and Septentrio heard us on this issue and performed some new development to allow the drone to stabilize its residuals during flight over a period of up to 10 minutes. And we get 5 to 10 centimeter drift levels over 10 minutes without using any sort of external positioning system. So those are some of the challenges and applications where we've been able to really raise the bar in the experience and quality that industrial customers can get from aerial imagery and data collection. Thank you.
Thank you, John. We're going to hear next from Flying Cam in absentia a little bit because Emmanuel Previnaire, the CEO, is off in China pushing the envelope with some new applications. But here to take over for him briefly is Gustavo Lopez again from Septentrio. Gustavo?
Thanks, Alan. Yes, I must apologize. It's sad for us that Emmanuel cannot make it with us. But they had actually an excellent video that they prepared for us, which I will give you the link at the end of this presentation so that people can also watch it. But let me just talk to you briefly, actually, what Flying Cam is doing. Flying Cam is, of course, a provider, and it's an already well-known provider of close-range aerial filming services. They mainly use, of course, great helicopters. If you take a look at the platform, it's actually fantastic. But they also use, they are starting to work in other type of UAV applications as well. So it's definitely exciting to get to the web page and to know more about them. The interesting part actually is that in the usage of GNSS technology, they are trying to use surely to monitor the position of the UAV platform, of course for the aerial filming side, and that's in the navigation side, but also in the positioning geotagging of certain elements in pictures as well. But they are also working in city operations. You have to think that they are filming in cities such as Paris, etc. So they are actually looking for technology that is much more reliable and where they can have some redundancy behind it. And they have excellent examples. Actually, they have already won quite some Oscars. And the examples is basically Game of Thrones, Mission Impossible in Paris, and of course the case of a GNSS, which is a new use case that will be explained shortly actually by Flavien from Altametris. And here's some just pictures actually that you can also watch in the video itself. You can see here how the Game of Thrones is actually filmed and how they actually need accuracy in order to have a reference of the 3D models that then they are presented in the films basically that you get to see. These are only of the pictures that you get to see. Here, for instance, you have the Grand Palais in Paris, where they were also filming parts of the Mission Impossible film as well. And that's the platform here below that you get to see, which is actually a helicopter that requires this reliability in this type of environment, which is basically the city as well. So if we want to talk about the technical challenges that Flying Cam had, of course, while filming the Game of Thrones, you have to think that they have to fly pre-programmed flights actually, because they need to follow certain paths basically in order to film the locations as well. And they need to have very high speed flights as well. I mean, we're talking about action movies, of course, so this is actually quite interesting to see as well. And you have to think that there are 500 people on set, so you need definitely the reliability and redundancy in the system that you are flying, right? This is, of course, quite important for them as well. They are making the computer imaging as a reference, so they use 3D models maybe already from the animations part, and they need to follow those, and they need to also do the geotagging of certain precision of images as well. In the Mission Impossible case, which was also in Paris in Grand Palais, they actually also covering two sides of the building of the Grand Palais. They need a high accuracy photogrammetry camera, and they need to have these precisions not only on the positioning side, but also in the orientation aspect as well. We have to think that they are taking around 1,000 pictures, which are geotagged precisely for creating a cloud point, which is actually a quite precise one. And something that was very interesting to hear, actually, and that you can hear in the video as well, is that they had actually problems of disturbances from magnetic field disturbances coming from the underground of Paris. And in this case, a dual system, a GNSS dual system, definitely will help them as well quite well. And this takes me, of course, to the last example, which is CNCF, which is going to be explained now by Flavien, and where they also have, of course, the importance of reliability due to locations with loss of RF disturbances. But this is the team. This is actually the link to the video, so I really recommend you to watch the video. It's an excellent video, so we will also put it in available for you as a link so that people can watch it and that they can hear, of course, the words from Emmanuel himself.
Thank you, Gustavo. Let's turn now to Flavien Viguier from Altametris. Flavien, please go ahead.
Yes, thank you, Alan, and hello, everybody. So I'm Flavien Viguier from Altametris, and I will present you the use of drones and what we can do with some drones for Altametris, so for railways application. What is Altametris? Altametris is a subsidiary of SNCF, which was specially developed to use drones and non-intrusive measurements for railway application. I will try to show you the link with us with Flying Cam, but also the need of GNSS solution for safety and security, but also for data analysis. So here you can see a small video about a project we've made with Flying Cam team. This project was made 2 years ago in the Septentrio of Marseille. The trouble of this project was that we are doing this acquisition during the football competition in France, so that was just impossible to imagine to deploy an helicopter in the center of Marseille and make a high accuracy acquisition. So in cooperation with Flying Cam, we have integrated a LiDAR from the Viguier company in the drone, and we have made surveying process of as you can see in the movie, it is a really dense site with lots of cables, lots of electromagnetic difficulties, and so that's why it was a really interesting project for us. So just to see, that was an introduction of what we can do with a drone. Just another slide which presents now what could be the use of drones for railway application, and you will see that in each of these applications you will be able to imagine what the importance of GNSS is. The first is land surveying and mapping. So the aim there is to be sure that the measurement you do give good results for our clients. So for this, it's more about precision and accuracy of GNSS. On the other side, we've got inspection of industrial sites, civil works, electricity, or earthworks. In this case, we can speak about precision and accuracy of the positioning to be sure to make good measurements, but also to be sure to make the acquisition without taking any risk. Sometimes for catenaries, for example, we can fly just 1 meter from the catenary, so it could be really dangerous. for the flight, especially due to electromagnetic interference. So we need a big reliability of our systems. And also, as you can imagine, we can use drones for railways to make some surveillance, so to detect intrusion in the network and avoid cable theft, for example. So in this case, that means we need to identify really precisely where is the intrusion, to say to SNCF police to go into the field. And last but not least, you can also make some consulting and explaining to railway and SNCF consultant that to ensure safety and security, you must use safe drones with high GNSS reliability and high safe drones. So I will go now in some presentation of the French railway network. So as you can imagine, it's one of the densest railway network in Europe, with lots of things to inspect, lots of train stations, and nearly 10 million passengers each day. For that, today, what is made is that SNCF is using trains, is using people on the field, but also on-field sensors. Everything works really well, but as you can imagine, with those techniques, you need to go into the track. So that means you are intrusive. There are lots of security impact for people on the field. That means so traffic disturbance, and most of those applications are really single user oriented. So that means you may make an acquisition for the rail. After that, you need to come back in some weeks to make an acquisition for the catenaries, and after that, for rockfall, for example. So it is really long and expensive. So for that, we had decided to use some drones. Why? Because in France, we are really lucky. We've got a really innovative legislation which started and which was created in 2012. For this, we've got two different kind of application. 4 scenarios, so scenario S1 and S3, which means that we can make BVLOS flights in urban area or in rural area. So that gives us the possibility to use drones in train stations, for example. And the most important scenarios for an infrastructure manager at SNCF with long tracks is to have BVLOS application, so S2 and S4. So that means we can fly with a drone for long distances up to 100 kilometers. We have already made that for SNCF. That is key for this scenario, to have, again, reliability of your GNSS and redundancy, to be sure that in every second of your flight, you know where your drone is, and if your drone is safe enough for this operation. So if I go more in details for BVLOS needs, and I can explain why those BVLOS are really interesting for SNCF. For example, as I mentioned before, today we use trains, but those trains most of time must do acquisition during the train traffic, and we can't see only troubles in the track. By using those airpaths, we could be able to optimize the maintenance process, and with that, we need sensors which are able to give us good data which respect SNCF specification. So we can, for example, explain trouble with vegetation monitoring. Is the first maintenance expense for SNCF. It's something about 8,000 hours lost each year for SNCF. So that means we need to use the system to cover thousands of kilometers in one flight and extract precisely vegetation. We can also use it to make ballast control or identify trouble with the truck with the super elevation or the misalignment. That's safety, definitely safety application for railway. So at the end, if the drone gives us good precision and accuracy, we will have better trains and safer trains. And as a typical scenario for the use of drone, we are now testing that in France, is that using a fixed-wing UAV, which can use a LiDAR system, which need to have a really high accuracy. That means in railway, we need to have something between 1 and 2 centimeter relative accuracy and about 5 centimeter absolute accuracy. It is mandatory to be sure that the results obtained are safe for SNCF. And so, as you can imagine, our systems and our tracks are located most of the time close to inhabited areas, even in cities. So when we deploy those drones, we must be sure that we will not see any flyaway. It will be just a shame for SNCF to have a drone which crash in a car or in somebody because the system is not safe enough, and most of this accuracy is based on GNSS application. In the same way, to talk about again GPS redundancy and GPS reliability, we can talk about city flights. In this case, you can see there the Gare du Nord train station, which one is the biggest of France and even Europe, I think. For this case, as buildings were too close to the trains, to the rails, that was just impossible for us to deploy drones. The French legislator say to us, if you use a drone today, drones are not safe enough due to a lack of redundancy in GNSS. So you must use an helicopter, an inhabited helicopter, a manned helicopter. So that means the French legislator consider it is less dangerous to use a 5-ton helicopter over Paris than a 20 kilograms drone in Paris, just because of GNSS reliability and capacity to avoid such kind of flyaway. So again, for such kind of project, you can imagine that we could be more reactive by using a drone. We can even imagine having some drones directly in the field, which can make safe control each day, and so a lot of redundancy of data, and see if there is some trouble for power lines, hydraulic networks, or even make some clearance control, so to see if the train can go into 1 or 2 tracks. Why I say that is just because in this case, as you can imagine, it's just impossible to make such kind of survey with trains or with people, because it's something about 2 or 3 trains each minute. So drones could be the only solution to improve our current process. And again, the typical scenario for that is that we will use some photogrammetric sensors and even LiDARs to be able to build in 3D the rail environment. So we will fly with a really low altitude and with a corridor which could be considered as a BVLOS corridor for drones. And as it is located in urban areas, safety is definitely mandatory. Today, the trouble for us is that when we fly in such kind of environment, we are not able to fly too close to buildings. So we are working with Septentrio, but also with Flying Cam, to improve safety and security of the drone. So based on the Septentrio board quality, we think that it will be possible in some weeks to improve the global safety of the drone and then avoid flyaway, be able to avoid it by considering that a level of risk of 10-7. So it will be a great new project for us, and that will give us new opportunities and new businesses for surveying and mapping of railway, but also inspection. So at the end, just to show you what kind of result we can obtain in railway environment, you see there a point cloud which combine LiDAR data with photogrammetric data. And in this point cloud, after that, so we extract the rails, catenaries, buildings, and we create a 2D map for project, but also a 3D map for clearance control, and at the end, some BIM, so building information modeling model for project exploitation, but also maintenance of railway infrastructure. So drone could be considered in such kind of project really agile and precise, and it will be a new step and a nice step to improve the cost of railway infrastructure monitoring. Thank you.
Thank you, Flavien. We'll turn now to questions from the audience, but just before we do, I want to assure everyone that, because I noticed that we had a surge in attendance about midway through the webinar, a number of people signed on. For those of you who have joined us midway through, you will receive an email after the webinar with a link to the full presentation. So you'll be able to get the full content. And we will also recap some of the content in a future issue of the magazine. All right, the first question for our panel, and this comes up in nearly every webinar or every GNSS topic, and that is, what do you do when there is no GNSS in a GNSS denied environment or an obstructed environment? How does your UAV platform handle being in a GNSS denied environment? What systems are presently available and suitable to deal with this problem, to fly, for example, under a bridge? We can hear first from Gustavo, and then anyone else who wants to join in, please do.
Thanks, Alan. I think indeed when we are talking about GNSS denied environments, I think of two aspects. One is indeed the actual environment where the drone is working, as you mentioned, under a bridge or in a difficult city environment. In that sense, I'm thinking, of course, of techniques in the GNSS technology. Of course, many people are already having their own algorithms in the multipath mitigation side. However, that sometimes might not be enough indeed. But something that we have seen definitely helping a lot is multi-constellation. And we have already lots of constellations. I mean, we are talking, of course, GPS, GLONASS, Beidou, Galileo, etc. And when a high-end GNSS receiver is really making use of this in order to have the performance, then you really have a platform that is much more robust. And I can tell you many GNSS technologies that just say, okay, we can track the signals or we can use the signals, but actually not everybody can do the same type of use as when we are talking about multi-constellation. And the other aspect is also we're bringing, of course, as I mentioned, the GNSS INS part of it. That means when you don't have GNSS, then the INS system helps you to do some costing system aspects as well. And then the other part, of course, in the night environment, of course, you will also think of aspects such as interference mitigation and anti-spoofing. And this is indeed something that many GNSS technologies are trying to bring more and more. And as I mentioned to you, it's not an easy task, of course, especially on the spoofing side. But there are also more and more systems coming there. Galileo, as an example, is trying to bring authentication that can help in those type of aspects. But also high-end GNSS technologies, for instance, in our case, the AIM+ technology that we have in Septentrio helps not only in the interference mitigation, but also to keep a proper signal even when you have a spoof element as well coming from an external side. And this is actually one more of my slides where I present basically how Septentrio receiver can perform versus other GNSS receivers as well.
Flavien, did you wish to add something to that?
Yes. In addition of what Gustavo said, we can say that most of the thing for positioning and to ensure good positioning in different difficult environment is to make some hybridation. So that means most of our systems are based in nice GNSS and precise GNSS, but we also combine this information with some SLAM technologies, so simultaneous localization and mapping by using some cameras. Or even we can use some LiDAR odometry and mapping, so we integrate directly in the drone some specific LiDAR to ensure that when we miss some GNSS signal, we will be able to make some relative positioning with the bridge. And the key point for that is to have a really nice hybridation to say, okay, when I lose the GPS, I can go through the SLAM or the LOM, and then when the GPS come back, I have no gap in precision and accuracy. And so that's really key point about hybridation systems.
Thank you. We're now at the hour mark, but I'm going to go a little bit past the hour because we have a couple of more interesting questions to get to. We'll be on for at least another 5 minutes. Second question, for getting the best positional accuracy with the drone, do we have to keep a base receiver during the drone flight period, or are there any other methods available? John, you wanted to speak to that first.
Sure. So there are kind of two levels that I can speak to off the bat, and I'm sure Gustavo can add what's coming down the pipe. Depending on your physical location that you want to operate in, many parts of the world have GPS reference stations that are available called CORS, continuously operating reference stations. These are often used for seismic surveying. For example, there are a ton of them here in California. Some are used as reference networks for rail or highway departments, and often the data is freely available. And so depending on the accuracy you want, if you're within 20 to 60 kilometers or so of one of those stations, you can download its data after the fact and use it to perform the same PPK corrections that you might do with an on-site base. The other technology, and this is one that I'm personally very interested in seeing if it can be developed and brought to market effectively, is called PPP, Precise Point Positioning. And this uses a corrections data stream that is broadcast from satellites in geosynchronous orbit, similar to how the NOAA WAYS or EGNOS satellite augmentation systems are delivered. But the data is collected from many more survey stations and can be used over time to get the accuracy of your position during capture down to the 5 to 10 centimeter mark. It has some trade-offs in usability. For example, once you turn on your receiver, you often need to wait 15 to 25 minutes to receive all of the corrections data and converge to the correct solution before you can begin flying. But I think this has a lot of potential for allowing anywhere in the world sub-decimeter positioning, especially for survey applications.
Gustavo, anything to add to that?
No, I think actually the answer from John is actually quite excellent. Indeed, the services such as PPP is something that is becoming better and better, and I think many companies in GNSS technology are investing in order to have these systems working not only on precision side, but in reducing the convergence timing as well, which is also requires some algorithmic work, of course, behind that side. And the other aspect, I think, which is what we are also trying to work with John, especially because he has a very interesting case on inspection, is to actually have a return to home, which basically which does not require a base station position inside, but it still gives you a very good reliability and accuracy, relative accuracy actually in a very short flight actually, which is actually more than good enough for their needs as well. So this is actually some technology that we are working on as well. But again, I think the PPP services is also definitely evolving very much in the industry.
Thank you. I want to reverse field before we go on to the third question, to go back to the first one about GNSS denied environments. Todd has something to add to what we have previously heard. Todd, go ahead.
Sure. I just wanted to point out that our current drones, the ones we use in Texas, are actually not doing well in GPS denied environments. We have a lot of work to do to make this a fully reliable system to reach something like the 1 part in 10 million that was mentioned earlier in one of the other presentations. That's a really high bar. And if you want to do this with visual processing, say if you're making a three-dimensional map using your camera, and if GPS goes down and you want to use your camera to orient yourself and locate yourself within the map, that turns out to take a great deal of onboard processing. You may be forced to use a large GPU on board if you want to do this in real time, or something along those lines. And so our current processing capability is exceeded by these demands, and we would be looking forward to a time when we could fit all of that processing on board. But currently we do our map generation after the fact.
Thank you. For our final question, one attendee wants to know, what are your experiences concerning the effects of vibration on the quality of survey or inspection performed with the UAV? Gustavo, you referred to this briefly, and I think John mentioned also that the UAV is its own best jammer. Can you give us any further insight into the problems with vibration and if there's any rule of thumb in terms of dealing with it?
Sure, Alan. I can actually start. Very interesting is to see that the technology that we are using, which is a high-end GNSS receiver, is the same type of technology that we have to use in tractors. And you have to think basically that these heavy machines, they have very, very, very heavy vibration aspects. This has been a challenge actually for Septentrio already through the different years in order to improve the technology in that aspect. And this is thanks to that actually development that we have done. We see that the same technology in a drone can help a lot. We call it actually the Log Plus technology, but it's also algorithmic side in order to manage your measurements and to make sure that your position inside is well handled. Again, also GNSS INS can also help, because then you have another element of an external sensor that is not only using information from the measurements of the satellite, and that can also definitely help you to compensate a bit of this aspect of vibration as well.
John, anything to add to that?
Yeah, so there are two places that we've had major challenges with vibration. So the first, on the specific positioning side, is that the GPS receiver is in many ways a function of its clock, and as an integrator you have to be very careful to give it a stable environment to operate in. Vibrations and sometimes transient stress, if it couples into the module itself, can throw the crystal and the time estimates off and cause a transient loss of lock that can introduce some chaos into flight. And so we've seen that and had to develop specific strategies for ensuring that the GPS actual module is given a very stable and isolated platform. The second place is how you're capturing the data. So with a large amount of vibration, if that affects the camera and blurs your input imagery to any degree, that significantly affects your ability to do photogrammetric reconstruction at a very high precision level. And so isolating at a minimum the vibration with grommets and other mechanisms, and even using active gimbals to cancel that out, are important components to think about when building a platform.
Thank you. Thanks, John. Thanks, Gustavo and Todd and Flavien, and also to Flying Cam for an excellent webinar. Thanks to Septentrio for bringing us the webinar, which we will now conclude. I would encourage attendees to review the webinar again at your leisure when you get the link to it submitted later, and also to share that link with any of your colleagues who you think might be interested. Next month, our webinar is going to be about protecting time-sensitive critical infrastructure systems. We'll have that on November 15th, and another one concerning LiDAR use in mapping and other applications on November 29th. This is Alan Cameron for GPS World. Thank you so much for attending. Thanks once again to our speakers and to Septentrio for bringing us the webinar. Allison, back to you.
Thanks, Alan, and thanks to everyone for attending today's webinar. If you have any more questions, do not hesitate to contact our presenters at the emails on your screen now. Links to their email addresses are also located in the bios at the left of your screen. You can share this presentation by clicking the social media icons on the left side of your console. Finally, you can find a PDF version of today's slides to download in the resources box on the left side of your console. You can also view Flying Cam's presentation on YouTube via the link in the resources box. An on-demand recording of today's webinar will be emailed to you tomorrow and will be available online at gpsworld.com/webinars. We look forward to seeing you at a future webinar.